Dr. C. Lakshmipati, Associate Professor of Physics, HNS Department, SRIT Engineering College, Anantapuram. Today we are discussing Unit 5, that is semiconductors. So semiconductors are which material allows the flow of current partially or moderately is known as semiconductors. Solids is classified into conductors, semiconductors, and insulators on the basis of band theory. Okay, so we know that already conductors means which material allow the flow of current highly, then the material is known as conductors. Which material allow the partially or moderately, then the material is known as semiconductor material. Which material does not allow the flow of current is known as insulators. So according to band theory, we have the semiconductor materials are two types, which is intrinsic semiconductor material, extrinsic semiconductor material. In the extrinsic semiconductor material, again two types, which is P-type semiconductor material and N-type semiconductor material. Intrinsic semiconductor material, the pure semiconductor material are known as intrinsic semiconductor material. That is example pure silicon and pure germanium. So in the pure semiconductor material. In the intrinsic semiconductors at T equal to 0 Kelvin, the valency band is completely filled and all the states in the conduction bands are vacant. So they act as insulators at at 0 Kelvin temperature. So for silicon, energy band gap is 1.2 electron volts and germanium has the 0.7 electron volts. So the diagram shown in the figure. So greater than the T greater than 0 Kelvin, the valence electrons occupy sufficient some amount of thermal energy. As a result, breakage of covalent bond takes place, releasing free electrons. These free electrons creates holes in the vacant positions in the crystal. These vacancies are known as holes. These free electrons cross the forbidden gap and enter into the conduction band. At T equal to 300 Kelvin, the energy band gap of silicon is equal to 1.12 electron volts. For the germanium, 0.64 electron volts. So as temperature increases, the width of the energy gap decreases and larger number of electrons occupy conduction band and shown in the figure. So extensive semiconductor material. Impurities semiconductor materials are known as the extrinsic semiconductor material. So based on the type of impurities, there are two types of extrinsic semiconductor materials are there. One is N-type semiconductor material, second one P-type semiconductor material. So next, N-type semiconductor materials is obtained by doping an intrinsic semiconductor material with pentavalent impurities atom like phosphorus, arsenic, and antimony. So the four valency electrons of the impurity atoms bond with the four valency electrons in the silicon semiconductor atom and the remaining one electron of the impurity atom is left free in the phosphorus. So therefore, number of free electrons increases as the electrons are produced in excess. Electrons are the majority charge carriers in N-type semiconductor materials and holes are the minority charge carriers. So since electrons are donated in this type of semiconductors, the energy level of these donate electrons is called donor energy level, which is close to conduction band. So the current flows in this type of semiconductors is due to electrons and shown in the figure. So P-type semiconductor material. P-type semiconductor material is obtained doping an intrinsic semiconductor material with trivalent impurities atom like boron, gal- gallium, indium, aluminum, etc. So the three valence electrons of the impurity atoms pair with the three valence electrons of the semiconductor material atom and one positive of the impurity atom remaining vacant in this called hole. So therefore, the number of holes increased with the impurity added to the it. So since holes are produced in excess, they are the majority charge carriers in P-type semiconductor material or electrons are the majority charge carriers. Since the impurity can accept the electrons, this energy level is called acceptor energy level. So, and is present just above the valency band. The current flows in this type of semiconductor is due to holes. So, properties. The conductivity of semiconductor material depends on its temperature and its increases with increasing temperature. The energy band gap of a semiconductor decreases with rising temperature. At 0 Kelvin, semiconductor becomes an insulator. So the absence of an electron in the valency band of a semiconductor materials is called hole. Hole occur only in the valency band or an empty electron state is called hole. So like electrons, the holes in the valency band also conducts electricity in case of a semiconductor material. The electric current in a semiconductor material is the sum of the current. So due to the electrons and holes. Hole is a positive charge carrier of current. Carrier concentration of density of charge carrier in intrinsic semiconductor. So deriving this equation, finally we get the carrier concentration of the charge carriers. So we want to determine the first density of electrons, density of positive holes, and finally we get the in this carrier concentration, that is Ni equal to 2 into 2 pi kt by h square whole power 3 by 2 me star mp star whole power 3 by 4 e power minus e by 2 kt. Then we get Fermi level in intrinsic semiconductor material. Then the Fermi energy level we get, what is that? E equal to EF equal to EV plus EC by EV plus EC by okay. EF equal to EV plus EC by 2 minus KT by 2 log ME star by MS star whole power 3 by 2. Then here E equal to EV plus EC by 2. Extrinsic semiconductor material. Impure semiconductors in which the charge carriers are produced due to impurity atoms are called extrinsic semiconductor material. Based on there are two types of intrinsic semiconductor materials are shown already discussed and shown in the figure. Okay, then we have the N type and P type semiconductor materials and charge carrier concentration. Next, we have the drift and diffusion current. The net current across the semiconductor material are two components, that is drift and diffusion current. What is the drift? When the external field is applied in a semiconductor material, each charge carrier experiences a net force, and so electrons move to the positive side and holes move to the negative side. This net movement of charge carriers is called a drift. The electric current density is given by J equal to NEVD. Next, we have the drift current density, sigma equal to conductivity, sigma equal to NIE mu N plus mu P. Next, diffusion. The movement of charge carriers from higher concentration to lower concentration region is called diffusion. So, in a semiconductor material, charge carriers may move either by drift or diffusion. So, under equilibrium condition, the charge density is uniform in the absence of electric field. So, if excess charges are given to the semiconductors by some means that the charge density becomes non-uniform. Then excess carriers moves from higher concentration region to lower concentration region. This process continues until the charge density becomes uniform. So, and it is called diffusion. Next, we have the diffusion current density of electrons is Jn equal to minus E into dn dou by dou n by dou x. Then the current density of electrons is the Jn equal to E dn dou n by dou x. Then the current density of the holes is diffusion Jp equal to minus E df dp dou p by dou x. Then the total current density of diffusion is J total diffusion equal to Jn plus Jp. that equal to E dN dou n by dou x minus E dP dou p by dou x. Then the total current density of a semiconductor material is J total equal to J drift plus J diffusion. J total equal to E into capital E into N mu N plus P mu P plus dN dou n by dou x minus dP dou P by dou x. Next, Einstein relation. So, Einstein shows the relation between the describes and the diffusion were directly related. So, those two parameters are mobility and the diffusion coefficient. The relation between the mobility and diffusion coefficient is known as Einstein relation. So then according to that, we can calculate the Einstein relation. That is dN by dP equal to mu n by mu p. This relation is called Einstein relation after the solving. Next, Hall effect. So when a conductor carrying a current is placed in a transverse magnetic field, an external field is proposed inside the conductor is a direction normal to both the current and the magnetic field. This phenomenon is known as Hall effect, and the generation of voltage is called Hall voltage, and derive the relation for Hall coefficient, that is RH equal to 1 by LA. That means the Hall coefficient RH equal to VHW by ISB. Okay, so applications of Hall effect. It is used to determine whether the material is P-type or N-type semiconductor. It is used to find the charge carrier concentration, that is RH equal to 1 by NE or N equal to 1 by RHE. So it is used to find the mobility of charge carriers, that is mu equal to sigma RH. So it is used to determine the electrical conductivity of a materials. It is used to design magnetic flux meters and multipliers on the basis of Hall voltage. So there we can discussing the direct and indirect band gap of a semiconductor, and the differences are shown in the table. Okay. So next, PN junction diode. So the combination of where the layer of P-type semiconductor material is placed with a layer of N-type semiconductor material such a way that the atoms of P-type combine with the atoms of N-type across the surface of a contact. Such a surface junction where combination has occurred is known as PN junction diode. So the combined P-type and N-type semiconductor with PN junction formation is known as the junction diode or PN diode. So the whenever the P-type material P-type is connected to the positive terminal of the battery, next N-type is connected to the negative terminal of the battery, then the bias is known as forward bias. So whenever the P-type material is connected to the negative region of the battery, then the N-type material is connected to the positive terminal of the battery, then it is known as reverse bias. Okay. Then in this chapter we discuss about the semiconductor materials, which is there are two types of semiconductor: intrinsic semiconductor material, extrinsic semiconductor material, and the charge carrier density and carrier concentration. And we have discussed about the drift and diffusion currents and Einstein equation, and we have the Hall effect and Hall coefficient and the applications of Hall effect. Finally, we discuss about the direct band gap and indirect band gap, and finally we have PN junction diode. Okay, thank you.